Well, hi to everyone and welcome to this DJ Instruments webinar. Okay, right now I'd like to introduce today's presenter, Eric James. Eric is the general manager of DJ Instruments and is responsible for the market development and growth of DJ's key strategic initiatives, as well as the oversight of all global operations. Now, prior to becoming general manager at DJ Instruments, Eric held both product management and engineering management positions at Hardy Process Solutions, another company within the Roper Technologies portfolio, where he established himself as a proven leader across all facets of product development. Now, earlier in his career, Eric also held various sales and engineering roles at General Electric, Nuvera, Fuel Cells, and Axons North America. He earned a bachelor's degree in chemical engineering from Lehigh University and an MBA from Northeastern University, where he specialized in marketing. Eric James, welcome to today's event. And with that, I'm going to pass things over to you to get us started. So, Eric, go right ahead.
Okay, hello, good morning, everybody. My name is Eric James. I'm the general manager here at DJ Instruments. I'm excited to talk to you today. I want to thank you for spending some time with us. Today, I'll be talking about pressure sensing in analytical instrumentation, or as I like to call it, the dead volume problem. So let's jump right into it. Today, I'm going to start with a quick DJ background. We're a small company, so it's good for you to understand kind of where we came from and what we're all about. Then we'll talk about some trends in analytical measurement. I like talking to customers. I like hearing what's going on in the industry, and I like tailoring my designs to the trends that are happening in the industry. So we'll start there, and then we'll go into pressure control and analytical equipment, where you use it, why you use it, just some of the basics. We'll talk about some pressure sensor offerings that DJ has, and then we'll focus on the meat of the presentation, which will be on flow-through pressure sensors, which are unique to DJ Instruments. So from there, let's hop right into it. DJ Instruments was founded in Massachusetts in 1971. We've kind of bounced around to a few different offices, so I never pin it down really. We're located in Billerica, Massachusetts now. And we are an original design manufacturer of strain gauge sensor technologies. We are capable of measuring pressure, torque, load or weight, and center of gravity is a unique one to us. We're really the only ones in the industry that have a true center of gravity sensor. We serve original equipment manufacturers by helping them solve some pretty complex problems, especially in the areas of pressure, load, and torque. And our key goal in designing sensors is to design something that helps add value to their product and isn't just a standard off-the-shelf type of product. We serve a variety of industries, life sciences, robotics, military and defense, even some performance sporting equipment with the torque. We've been in industrial packing machines, and we do a lot of test and measurement applications across the U.S. We also have manufacturing capabilities in both the U.S. and Malaysia. So that gives us the opportunity to start here on a small scale and really get the processes right, get the controls right in terms of how we're making the product. And then we can scale it up and outsource it to some low-cost manufacturing centers, which is really nice for us. A lot of the low-cost manufacturing capabilities that we have actually came as a result of our acquisition by Dynisco in 2007. We were bought out. A couple years after that, we really took a focus on implementing a lean manufacturing culture. So that started sometime around 2010. And really what that enabled us to do is give ourselves a really strong base to grow off of. We're a small company, but we're thinking big. We have the processes in place to scale cheaply, and that helps us pass on some lower costs to our customers, and that's a pretty good value proposition for them. I received a really nice compliment the other day from someone who was touring our facility, and what they said is, it's really nice to see somebody who's working smart and not hard, and that's really the focus that we take into our manufacturing philosophies. So DJ is a small company, but we have big capabilities and we're capable of doing quite a bit. I hope you see that as we go through this. In addition to really efficient manufacturing processes, DJ is also very focused on customer engagement and getting past the superficial level where we're just a product company. As an original design manufacturer, we don't really do off-the-shelf components. Most of what we do is custom design. And as such, we have to be pretty close to our customers. And as I mentioned earlier, one of the things I really like is talking to them about the things that they see in their industry, because it helps me design my core technologies around things that are going to offer value to their solutions. Now, in the previous slide, I talked about pressure, torque, and load. From here on in the presentation, I'm really just going to be talking about pressure in analytical measurement. So with that in mind, as I'm out there talking to customers and getting a feel for their businesses and their challenges, I've noticed some mega trends as of late, and DJ has a pretty good representation within the high pressure chromatography business. And, so as I talk, I'm going to kind of be tailoring this discussion a little bit towards the chromatography market, but it's certainly applicable outside of that. And honestly, I would love your feedback at the end of this presentation. If you think, I've missed the mark, or if there's some things that I haven't thought about that I should be thinking about, then I would love to hear that feedback from you. I think my contact information should be at the end of this, so feel free to reach out to me directly or ask a question through the webinar, and hopefully we can cover some of that stuff. Anyway, back to the point. So my conversations have revealed a couple things. The first is I seem to see that there are two segments within the chromatography business, but there's diagnostic users and there's discovery users. And I think manufacturers of equipment serving those markets, serving those users, are really struggling to differentiate themselves based on measurement speed and measurement sensitivity, because those two are sort of opposing forces. Diagnostic users, they want faster measurements. They know, kind of what they're looking for, what they're, what the separation technique is, and they want faster measurements of repeated samples, so to speak. Discovery users, on the other hand, these are the guys in the lab that are trying to break new ground, find new information, and the more accurate and more informative measurements they can pull out, the better. And on top of that, the samples that they're running are just getting more and more complex. The technology is just going to such an amazing level. So it's interesting to see how the manufacturers that I sell to are dealing with those problems. The second trend that we see is manufacturers are really looking to leverage design commonality. And what I mean by commonality is things that they can port from one system to the next with very little engineering development. It's almost like building modularity into your system to just make it easier to scale and change things. The real value for them in this commonality is that it reduces development time and cost, so that's engineering expense, and it increases the focus of their engineering efforts. Really, as a manufacturer of analytical equipment, you want to be focused on the end user. You don't want to be focused on the non-value added development for as much as you can. And one of the things that's driving that is that end user knowledge of analytical techniques, like the real hard science behind these instruments, is decreasing at the user level. And that's creating a higher demand for things like ease of use features, data analytics. So it's a lot more software development and a lot less hardware development. And I think, the best in class manufacturers that I'm talking to have really heard that and understood it, and they're looking to create commonality between their designs on a hardware level. Another one is that, with all of the differences between diagnostic users and discovery users, manufacturers can't put out different systems to meet the needs of every single user. So they're really looking to manufacture and design new instruments that can reach a whole broad spectrum of users. And that just helps them keep costs down, and it also helps with the end user. Having too many choices sometimes isn't a good thing, and I think the good manufacturers that I talk to, they recognize that as well. And the last piece is that lab space in general is becoming just more and more expensive. it's coming at such a premium. Everybody wants to put an instrument in a lab, and there's a lot of competition for that bench space. And I think manufacturers are responding to that by trying to miniaturize their equipment. I've even talked to some that are looking to make portable equipment, which is just, that would really change some of these markets that we're talking about here. So just some interesting mega trends. And, again, as I think about these trends, I think, how can I design my products so that they're in line with what the manufacturers are really trying to do? And I hope you see that as we go through this presentation. So with the industry trends as a background, let's take it down a level and start talking about pressure control within analytical instruments. Now, again, we serve a lot of chromatography companies, manufacturers, and so that's the industry I probably know the best. And so what you see on the right here is a simple flow diagram for how customers use pressure measurement. Now, most manufacturers will use some combination of pressure and flow and speed control of their pump in order to get the right mixture at the right pressure to the either separation or measurement part of their instrument. Flow measurements are usually coupled pretty close to where the actual analysis is done. The reason for that is you want to make sure you have the right flow at the analysis, and you want to make sure that the mixture is right. So sometimes you might have more than one stream coming together, and you want to make sure that you're getting the mixture right. Now, pressure, on the other hand, is usually measured as close to the pump as possible. Couple reasons for that. I think the biggest one is that the pressure is highest right at the exit of the pump because it's furthest upstream. So if you're gonna have a pressure spike, you want to know, what the max is that you're going to experience. And a lot of time, pressure measurements are used not only to maintain the system pressure, but also to ensure that you're not breaking anything. So it's almost a shutdown mechanism where pressure measurement runs too high, you shut the pump down, and that way you prevent damaging any of the components in your system, and especially the expensive ones like the measurement or the pump itself. Putting this into practice, a measured loss in flow rate causes the pump to increase speed. That's the basics of how the algorithm works. So the flow measurements is I don't have enough flow. It tries to increase the pump speed in order to make up for that flow. Now, in the event of a blockage, your pressure sensor is going to notify you of that blockage because the flow sensor is just going to say, hey, I don't have enough flow, keep increasing the pump speed. Whereas the pressure sensor is going to notice that the pressure of your system is increasing. Now, you want that direct feedback because it is the fastest way to get a safety shutdown on the pump to make sure you don't break anything. The other thing a pressure sensor does is by monitoring the pressure over time, you can start to pick up when there's accumulation in the system. So if there's something that's causing maybe scaling on some of the inside of your tubing, something like that, where your pressure's increasing but your flow rate is staying the same because your control algorithm's doing what you hoped it would do, monitoring that pressure sensor can alert you when predictive or preventative maintenance is required. And it can do that before the blockage event occurs. And obviously a blockage event means downtime for your customer. So that's why most customers use a combination of flow and pressure, because it allows you to control flow, it allows you to protect safety, and monitor your system's performance over time. One variation to the flow measurement scheme that I've been showing is to actually use two pressure sensors in series with a flow restriction in the middle. Essentially, you use the pressure drop combined with the size of the orifice or flow restriction to measure the flow. Where I see this a lot is where customers are looking to save on cost, specifically in nanoflow and microflow applications. Essentially, the flow sensors required to measure flow this low are pretty expensive, and customers will use a cheaper pressure sensing solution to measure the flow and control the pump speed based on that. These algorithms, they're not terribly difficult to get right, but they do require a little bit more upfront engineering work. And the good news is that they are pretty easy to scale between different flow rates. So to move it to a new instrumentation, it's not perfect in the sense of commonality, but it does get the job done. The only real drawback to this is that using a flow restriction like that actually robs some of your pump functionality. So you need a higher pressure pump than what you would if you didn't have such a high flow restriction. But this does save on cost. Two pressure sensors are usually far less expensive than a flow sensor. We see, maybe 33% of the cost in terms of material. So once you've done the upfront engineering, you get some cost savings over the life of the product. An alternative to using a combination of pressure sensing and flow sensing is to try to write an algorithm based on pump power consumption or pump current draw. Now, I have seen some customers do this effectively. I think the one complaint that typically comes up from customers who've tried this is, number one, it is actually quite difficult to get right. And number two, even if you do get it right, it's a lot more costly to engineer and develop than just using direct pressure control. Pressure control is just so simple. You get an analog signal, and you take that signal in and you linearize it to a pressure measurement, and then you can set your high and low alarms and shutdown events, that sort of thing. The other thing that I hear is that using a current draw or a power consumption measurement from the pump, it adds lag time into your control loop. And by the time your pressure measurement is made, sometimes that's too late, especially in the event of a sudden blockage where you get a very quick ramp of power consumption. So from a control standpoint, it's not really as reliable as a pressure sensor, and it's also very difficult to implement. The other thing is it doesn't scale well. And when I say scale, what I really mean is when you've designed one instrument and you've gone through all this work to get your pump control algorithm right, if you're changing pressure or if you're changing flow rate and it requires you to use a new pump and a new design, that means you have to rewrite that control algorithm. So again, we talked earlier about commonality and how the good manufacturers are trying to leverage commonality of hardware between their designs. It's much easier to replicate a design that uses pressure control over a power-based pump control. So again, using a pressure sensor, it provides more reliable control, it's easier to implement, and it can be replicated more quickly into new system designs. And I think that's why more manufacturers are using pressure control than pump power measurement consumption control. Okay, so now that we've established why you use pressure sensors and sort of the basics behind how you use them, let's talk a little bit about what DJ Instruments offers. So we offer two types of pressure sensors. One is a flow-through sensor, which is specific to DJ, and the second is a diaphragm sensor. You see these all over the industry, variety of different markets and applications. So let's start with our flow-through. A flow-through sensor, and I'll get more into the technical details of flow-through sensing in a minute. The main advantage of these is that they're mounted in line with the flow path, and what that means is that there's no dead volume inside the sensor, so there's no places for contamination to get stuck. The other advantage is they're very small. Their internal volumes come in two different sizes. One is 13 microliters, and then we can get down as low as 1.6 microliters, and that has a lot of advantages in analytical instrumentation usage. And they're miniaturized for ease of installation and for a whole variety of other reasons. Now, we offer a few different diaphragm sensors as well. So we offer flush mount and dead end, and I'll get into what that means in the next slide. These as well, miniaturized for installation. What DJ does really, really well is miniaturize the sensors. And we talked earlier about how a lot of instrumentation manufacturers are moving towards smaller and even portable size equipment. we're really ahead of the game when it comes to that, and we do try to keep things in as small a form factor as possible. So I'm going to walk you through the three types of pressure sensors that we sell. The first is a traditional pressure sensor, a diaphragm sensor. I like to also call it a deadhead pressure sensor. Basically, these sensors are mounted perpendicular to the flow, and they have a large cavity. Usually they involve some sort of T-fitting, and you screw the sensor itself into the T. And you can see in the diagram the flow direction and just that large dead volume space. Now, when you're taking a complex sample measurement, the last thing you want is for something to get built up within your system. Now, a lot of manufacturers are doing some pretty advanced cleaning processes. And if you have these dead volumes, it's really hard to clean out the dead volumes because you can't get flow through them. I mean, really, to clean out a sensor like that, you would have to remove the sensor from the fitting, and that's a pain, and it just causes the user a lot of headaches. So they try to get around that. One of the ways that they do that is by using a flush mount pressure sensor. These do a little bit better job, and really they're screwed into the flow path. So same idea using a T-fitting, but they get right down into the flow path. And they try to minimize the dead volume to the extent possible. But as they are in the flow path, there are points, basically on either side of the flow path where material can get built up. And when material gets built up, that can actually affect the accuracy of your measurement. Because as the next sample comes through, it could pull something that wasn't actually in the sample, and where especially your diagnostic users, or I'm sorry, your discovery users are looking at very trace concentrations of substance. You don't want to pull anything through that wasn't in the sample. So a lot of the manufacturers that we work closely with, they recognize that they have to eliminate these points of dead volume in their system. And it's not just around their pressure sensor, it's in the way they run their tubing, in the fittings they select. Everything goes into that. So the solution to that is a flow-through sensor, and let's take a look at what that looks like. This is an oversimplified diagram of what a DJ pressure sensor looks like. Now, as I mentioned earlier, DJ sensors are mounted in line with the flow path, and they're just really well engineered to eliminate places for contamination buildup and to eliminate dead volume. You can see that the tubing goes right into the sensor housing and it fits in without any dead volume, and that it comes out the same way. It's a pretty simple design, and the sensor is in the housing itself. The other advantage of this is it allows us to eliminate the internal volume to the extent possible. And as I mentioned before, our sensors have internal volumes as low as 1.6 microliters, and we're looking at how to get even lower. What that helps customers with is it helps them increase their sample speed without increasing the flow rate. When you increase the flow rate, a lot of times you're using substances to move the sample along into the measurement chamber, and increased flow rate can actually reduce your measurement sensitivity. So when you're looking to get a discovery user a really accurate and informative measurement, you can use less material to push the sample along. So that reduced internal volume absolutely helps manufacturers get the most out of their equipment. So, a couple flow-through sensor basics. Number one, wetted materials, we have a whole bunch of them. 316 stainless steel is our big one. We also do a lot of titanium. Titanium's a lot better for lower pressure applications. And we also have some other non-reactive wetted surface materials. So if there's something for your process, I know, for example, ion chromatography, you pretty much can't use anything metal. So we'll talk a little bit more about that in a few minutes. But if you have an application like that, we can handle it for the most part, or do some development to make sure we can handle it. So we handle pressure ranges all the way up to 30,000 psi. We've done higher than that. It's a little tricky to hold that kind of pressure, but we have done higher than that before, but standard up to 30,000. Good accuracy specs, combined error 0.25% a full scale, and as I mentioned earlier, internal wetted volumes of 13 microliters or 1.6 microliters, depending on what your application needs are. We also have done a lot of work with reducing the size of our total package volumes. Our smallest right now is less than a half a cubic inch, so that's pretty good for systems that need to get smaller and smaller. Finally, the sensing elements, they're designed to be used with a whole number of fittings. Our standard fittings are 1032 or quarter by 28. We can do 16th inch NPT, and we do have experience working with Viper fittings. I know a lot of customers are using those nowadays just because they're a little easier to work with. And finally, all our flow-through sensors use a proprietary foil strain gauge. That's the basis for the technology. With the specs established, let's move on to the value of a flow-through sensor. The first thing is it helps customers achieve sample measurement accuracy. Again, we're talking about the zero dead volume here and how it eliminates places for contamination materials to build up, so you don't get stuck material that affects a subsequent sample. The last thing you want in a measurement application is to run one sample and then run the next one and have the one before it affect the measurement of the second sample. So having no dead volume within the system really helps with that. The second is having a flow-through sensor simplifies the cleaning process. We talked about this earlier, but during the cleaning, if you have a bunch of dead space, you actually have to remove the sensor to truly clean it out. It's hard to just flow material through it to get that cleaning. So a flow-through sensor allows you to clean the process much simpler. The second thing is we help manufacturers achieve lower internal volumes, and that lower internal volume means that you can get better measurement accuracy through less dilution of the sample, so it takes less motive fluid to push the sample through. And it also helps increase the speed without increasing the flow, as we covered, because flow can lower the sensitivity. Another advantage is the small form factor of DJ flow-through sensor really helps manufacturers get to those smaller size instruments and the portable size instruments. And then finally, a flow-through sensor is very simple to integrate, so it allows for commonality and cost leverage between large systems, small systems, higher pump flows and pressures, lower pump flows and pressures. It's really very modular and allows you to scale up and down very quickly without having to re-engineer the system. One point of note is there's no sensor size difference between pressure ranges, so whether you're buying a 1,000 psi sensor or a 30,000 psi sensor or anything in between, your package size is going to be exactly the same. So that helps from a design standpoint, and our customers really enjoy that. This is what our flow-through product suite really looks like. It's a 4 sensor block, and there's a ton of configurations in this, as I mentioned, with all the different metallurgies, different elements for the pressure sizes, even if they're all the same. But there's 2 basic packages. There's your large housing package, which is just under or just over 2.5 cubic inches, and then there's a small package called the DFI or the LVI, and that's under 3/4 of a cubic inch, and I'm going to talk about one that's even smaller than that soon, that's coming out next year. The other thing that you have some variability on is which element you select. Obviously going down to a 1.6 microliter element, there's a little more cost in getting the fine manufacturing capability for that. So we basically have a low volume package or a standard package, and in 2 different housing sizes, but the capabilities are mostly the same. So it depends, what's best for your system, and we just like customers to have a couple choices into what they're picking out. So the DF line or the LV line, they both perform just about the same, and really good products. Customers are happy with these. Now, with our quote standard offerings kind of outlined, what really separates DJ is our design to fit program. So I really believe that DJ does its best work when we're involved in customer projects at the start of a new design. We really match our development cycle with our customer's development cycle, moving from design to basic prototype and test to a pilot production run and then production run. As we match to the customer product design, we can make little tweaks along the way that really help add value to the customer. We can do custom electronics design. We have a wide range of analog, digital communication options. We do custom cabling, everything from your standard Ethernet cable to an analog cable, everything in between. We've done some really interesting project work on the cabling side to connect more easily with a customer platform. And then mechanical design. I pointed out the DF and the LV packages on the previous slide, but if that doesn't work for you, we just need to know what does, and we can design a mechanical housing to fit. And again, we've had some really cool projects where we've done some different mechanical designs for specific customers. The end result of our design to fit program is a sensor designed for your specific equipment. And the best part about having that is that we would protect that for you. We would only resell through your aftermarket, and your competitor wouldn't be able to purchase and integrate it. So it's good for customers who want that and see the value and the intellectual property in having a custom sensor. Now, I do want to take a few minutes and talk about some new products that I'm excited about. We have about 5 minutes left here in the presentation, and just two things I'm excited about. The first one is just a really miniaturized package and an improved package we're calling the DIFI or the Diffie. The form factor is about 0.3 cubic inches, so it's really tiny, really designed well. And it also has a differential output signal, which is different from our standard single output signals. What that does is it helps us reduce the noise of the sensor. It's amazing when you're installed in an analytical instrument how much noise you pick up from some of the surrounding instrumentation. I think it's just a factor of trying to stuff a lot into a small package. So we're designing something with some lower noise, and we also think that's going to help improve our performance at lower pressures. Our target really is to get down to the 0 to 100 psi range. Right now, our sweet spot is above 250 psi, I would say, all the way up to 30,000. And this small form factor, as I mentioned earlier, our elements are largely the same size. It's just the internal volumes that change. So it fits both the DF and the LV style elements. So you can do your cheaper 13 microliter version or the 1.6 microliter if you're really worried about that internal volume of your system. We expect this to be available Q1 of 2018. So launch is right around the corner, and we're excited about that. And we hope you are too. The other new piece of core technology that we're working on is specifically designed for the ion chromatography market. I think I mentioned earlier in the presentation about how markets like ion chromatography really just can't use metal. So we're coming up with an inert flow element. It's based on the DF size element, but it doesn't use any metal. So we have a little basic 3D printed prototype of our DIFI here. It'll fit inside that package, but it won't be a metal element. It'll be something a little different and unique. But we're excited about that as well, and we're talking to customers already about where that would fit into their systems and what the value of that would be. And that concludes today's presentation. Again, I really want to thank everybody for taking the time to listen today and to join in. I look forward to hopefully talking to some of you after this concludes. I'd now like to hand this back over so we can begin the question and answer period.
Okay, now let's get to the Q&A. We do have time for some questions. Okay, our first question is, what communication protocols do your sensors use?
So most of our sensors just use a standard analog output, 0 to 5 volts, in that range. We can set the span accordingly, but really it just comes down to what you need. As an original design manufacturer, we have all sorts of capabilities, and we could do I2C or SPI. We could even do some more complex digital protocols. So it's really just about what you need.
Next question. You mentioned load and torque sensors. Where can I find more information on those?
Sure. So we have some information based on located on our website, www.djinstruments.com. We also have a LinkedIn page that we're starting to put more content through. I would say the best way is just talk to one of us, either go through the website and submit what your application is, and we can talk from there. Or email me directly at eric.james@djinstruments.com.
Next question. What is the accuracy of one of these pressure sensors?
The accuracy, as stated, is 0.25% of full scale. That's a combined accuracy, including nonlinearity and hysteresis. All of those specs for our flow-through sensors, we actually have drawings on the website. So again, djinstruments.com, you can see more of the actual technical specs and how we configure some of our standard options.
Next question, do your sensors hang off the process tubing?
Do they hang off the process tubing? So the housings have mounting capabilities. So there are places where you can bolt into the actual housing so it doesn't completely hang off. We have seen some people do that where they're able to hang it off the tubing. The only thing about that is there is a possibility that you lose some accuracy when you do that, because if you torque the housing, the sensor is going to pick up on that. So again, that's something we can talk about as we go through the application.
Next question, how big are these sensors?
How big are the sensors? Well, the DFI, the one that we went through, was really small. I think it was 1/2 inch by 1/2 inch. But we have some larger housings. Our standard offering, the DF2, is probably about 1 inch tall by 1/2 inch wide, something like that. Maybe 2 inches tall now that I think about it. Still not very big though.
Any flow-through development for vacuum and low flow? The application is medical device blood contact.
I would be interested in talking about that a little bit further offline. Right now, we don't have a vacuum. Low flow is not really a problem. I mean, most of the stuff we're doing now, one of our good markets is nano flow. So low flow isn't a problem, but vacuum's a little trickier in terms of materials. We'd be happy to talk to you a little bit more about it, though.
Well, we're going to wrap up this webinar right there. Thank you to our presenter and for spending some time with us today. And thank you to all of our audience members for being part of this webinar event. Take care, and we will talk to you soon.